Sound check, sound check. All right, chemistry, we're moving on to the next lesson in the solution stoichiometry unit. This is day 55. You have the same cover sheet with the formulas as you had for day 54. And now we're going to move on to some problems a little bit more sophisticated. All right, so I'm going to do the A problems. So 1A, what is the molarity of 5.4 grams of NaCl dissolved in a 0.24 liter solution? So again, you have to come back here and understand what molarity is. It's moles of solute. In this case, it would be the NaCl per liters of solution. That's the water plus the NaCl. It's everything together. Okay, so we're going to come over here. So our target is you're going to break out this derived unit called molarity into moles of solute over liters of solution. We're starting off with 0.24 liters here and 5.4 grams. So we come over here and we write down what we're given. You have 5.4 grams. But as with many of these solution stoichiometry questions, you also have a denominator that you're starting with, and that's the 0.24 liters of solution. Okay, so let's look at what we have and what we need to get to. So on the bottom, we have liters of solution, liters of solution. So we don't need to do anything on the bottom. The units, again, all you're looking at is the units of measure. They are the same. Up here you have grams of NaCl. Over here you have moles of NaCl. So you're going to have to convert from grams to moles, and you've done that 1,000 times. It's called a molar mass conversion. And let's write out what that is. I'll write it up here. Okay, 1 mole NaCl equals 58.44 grams of NaCl. One of those is going to go on top, one on bottom. I think you all know which one it is by now. So grams of NaCl cancels. What you have left is moles of NaCl on the top, and you already had liters of solution on the bottom. So now multiply everything on the top, divide by everything on the bottom. And that gives you 0.39 moles of NaCl for every liter of solution. And of course, the proper way to finish that up, it's to me not wrong if you don't do this, but change it back to capital M. It's molarity. And that's your final answer. 1B is the same type of problem. I'm going to move on to problem 2A. So let's read that. You want to create a 500 milliliters of a 1.2 molar NaOH solution. How many grams of NaOH would be required? That's a very typical lab problem where you want to make this solution, you have to go back and figure out how many grams of NaOH. You go back to the storeroom, you get out the NaOH, how many grams of it are you going to need to make 500 milliliters of a 1.2 molar concentration solution. Okay, so it's how many grams, so we're going to come way over here, and I mean way over here. Grams of NaOH. Okay. Now, we've got the 1.2 molar. Whenever you have a molar that you're given, a molarity that you're given, you almost always start with that. This 500 is going to be an intermediate number that you're going to use. So I'm going to come way over to the left, and I mean way over to the left. You're going to need a lot of space on this problem. All right, so Again, solution is the NaOH plus the water mixed together. So that's your molarity, 1.2 molar. All right, so let's look at what you got. You got moles of NaOH over liters of solution. Over here you have grams of NaOH over nothing there. So let's start with the top. We need to get from moles to grams. All right, so we need a molar mass. Since I don't have to do this problem, but you do, I'm going to write what that is up here. Okay, so there's my molar mass. I need moles to cancel out, grams to appear, so you all know how to do this by now. Moles of NaOH cancel, so now you have grams of NaOH on the top. That's what you want. So you're done with the top. You did the top first, you've taken care of it. Now the bottom. Okay, so I have 1 liter here and nothing here. I need to get rid of the 1 liter, and I have this 500 milliliters to work with. So the first thing I want to do is convert this liter into milliliters. And it's specifically of solution. Again, 1,000 milliliters equals 1 liter of anything, but we're interested in solution here, so we're going to write solution with our conversion. So liters of solution cancels with liters of solution. Now we have milliliters of solution down here on the bottom. We want to end up with nothing on the bottom, so we're going to take the 500 milliliters and put it up on the top on the next conversion. That's all you need to write. If you want to, and you make it a ratio, you can put it over 1. That's fine. Anyway, milliliters of solution cancels. So we no longer have any units on the bottom. That's what we want. So it's going to be 1.2 times 40 times 1 times 500 divided by 1 divided by 1 divided by 1,000. And that gets us 24 grams. So you'd need to put 24 grams in to 500 milliliters of water. Really, that's going to make the volume increase slightly. And that would give you 1.2 molar NaOH solution, okay? The way you mix this, by the way, is so you end up with exactly 500 milliliters of solution, is you put the NaOH, the solid NaOH in first, and then you fill up the water until it's at exactly 500 milliliters. If you fill up 500 milliliters of water and then put this in, the NaOH, it's going to end up being more than 500 milliliters, okay? So you add the solid first, and then pour in the liquid second. That's a little lab technique. Okay, you do 2B, go on to 2C here. It's the same exact type of problem, so that one you're going to do these two. So I gave you 2 problems. There's a B and a C. Anything above A is a problem you do. So I do the A problems, you do the B and C problem, okay? Now we'll move on to 3A. What is the molality of 3.7 grams of LiOH in 356 grams of water? Okay, so you come over here and write down what molality is. Go back to the cover sheet. Molality is moles of solute over kilograms of solvent. Okay, so we're going to come over here and write that down here. And the solute is LiOH. Over kilograms of solvent. The solvent is the water. It's not the solution. Okay, this is not molarity. It's molality. So it's kilograms of H2O. Okay, so what are we starting with? Well, Okay, so we're starting with these two numbers. Way over. Okay, so we have grams of LiOH mixed in the solvent, which is grams of H2O right there, okay, and that's what it was given. So we have to get from grams of LiOH to moles of LiOH. Again, that's another molar mass conversion. So let's go ahead. I'm going to figure that. Again, you need to use this space, but I don't have to, so I'm going to come write it up here. And let's pull up the periodic table. And that's not it. There it is. Li is 6.94. You see it up there, element number 3. O is 16. H is 1.01. And I'll go ahead and write the total right here. Write the equivalency. Okay. And we got 1 mole that all adds up to 23.95. Okay, there's your equivalency. So you need grams to cancel out. So in the next conversion, and we're working on the top first, we're going to put grams on the bottom. Moles on the top, grams LiOH, grams LiOH. So now we have moles LiOH. That's what we want on our final answer for the top. So we're done with the top. Now we got to convert grams to kilograms, and that's a standard conversion for any substance. 1,000 grams is 1 kilogram. And in both cases, we're interested in water, so we put the substance. It's true of anything, but we're interested in H2O. So grams of H2O and grams of H2O cancel there and there. So on the top, we have moles LiOH. On the bottom, we have kilograms H2O. That's what we want. So we'll now go ahead and do the numbers on that. We'll now go ahead and do the numbers on that. And what we get is equals 0.42. Okay, and that is a molality, so it's 0.42 small m is your final answer. Okay, you go ahead and do 3b. It's the same thing. Okay, number 4a, what is the mole fraction? That's chi of 25.5 grams of KCl in 332.4 grams of water. So come over and look at the formula for mole fraction, and it's moles of one solute over moles of all solutes in the solvent. The key word is mole. And over here you're given grams of both. So you're going to have to do molar mass conversion for both of these and get them in the moles. So you do that before you really even start the problem. And mole fraction is dimensionless. All the moles cancel out, so you just put equals underline, and there's no units of measure there. It's just going to be a decimal number that you're going to get. Okay, so let's go ahead. I'm going to calculate the molar masses. So let's look at it. K, potassium, is 39.10, and chlorine is 35.45. So that gives us 74.55 grams per mole for potassium chloride. And water is 18.02. So we know that one already. And that's grams per mole. Okay, so now what we have to do is figure out how many moles is that many grams of KCl. So we're going to come over here, and we really don't do this in one long equation like we've been doing really with almost everything up until now. We just got to figure it out in bits and pieces. Partly because there's a plus sign in the denominator here that we have to use. We saw that if you're going to add all of these moles of solutes and solvents, you're going to be adding them together. So let's go ahead and do KCl first. Grams KCl cancels, and we have 3.7 divided by 7.45. 74.55, get that right, and that's 0.5. 0.05 moles KCl. Okay, for water, do the same thing. It's 132 grams. I'm going to divide this off here. So grams of H2O, so it's 132 divided by 18.02. And it gives us 7.3. Okay, and as you're seeing, you might want to do this on line paper, okay? I gave you a fair amount of space, but it might not be enough. So we figured out how many moles of KCl we have in 3.7 grams, how many moles of H2O we have in 132. Now we have to take the moles of KCl. It wants to know the mole fraction of KCl. So I'm going to do it up here. Again, you can't do that because, whoops, I blew it. I was supposed to do 4A. I did 4B. So you're going to do 4A, okay? But I'm going to do it up here. All right, so I've got, what do I have? 0.5. I'm not going to write moles. It's just because they're going to cancel out anyway. That's of KCl. Down on the bottom, I have 0.05. Plus the 7.3 for water. And again, all the moles are going to cancel out for everything. So now you do that math. Add the 0.05 to 7.3. And that gives you 7.35. Okay, so it's going to be 0.05 divided by 7.35. And that's going to give us 0.006. And that's the mole fraction. So chi equals that. All right, there's no units of measure for that. Okay? So you're going to do 4A because I mistakenly did 4B. It doesn't matter, they're both the same. Okay, we're moving on to problem 5. I love this problem. You're going to hate this problem, but you're going to learn to love it because it's going to teach you. This is really almost a beyond AP level problem. They would not give you a problem I don't want to call it complicated. It's just you have to learn how to do it, okay? Nothing about it is complicated. It's just doing it. And that's why I have you do it 3 times. There's a 5B and down below is a 5C version. All the problems are worded exactly the same, except the numbers are different. But there's a lot of stuff here that's really good to know. In fact, so much so I'm going to do this on line paper. Okay, here we go. Seawater has a density, so now we're getting into a problem that has density of 1.027 grams per milliliter. It is comprised mainly of sodium chloride and water. So it's really an NaCl and water problem here. What is the molarity of a solution that is 3.5 mass percent sodium chloride? So that's a second new concept here, is that you have to deal with a mass percent. And that's a tricky one, and almost nobody figures out how to do that unless they're told. So I'm going to tell you. So here we go. So what we're looking for is molarity. And so I'm going to write that down here because I want to write some things up above, and I'm going to do this on line paper. So it's moles of the solute, that's the NaCl, the salt and salt water, for every liter of the solution. That's the water, H2O, and the salt, NaCl, mixed together. Okay, so that's what we're looking for in our final answer right there. Okay, now let's take this one step at a time. Seawater has a density of 1.027 grams over milliliters. So I want you to write that as a conversion factor. And you don't have to even write the equivalency first, you can just write it. It's simply this: 1.027 grams of, and what is it of? Seawater. So that's of solution. So it's grams of solution, not grams of the NaCl. It's grams of solution for every 1 liter of the solution, the salt and the water mixed together. Okay? So of course now we can write the other equivalency. We'll go ahead and do that. It's put the or, if you want to put that there, 1 liter of solution over 1.027 grams of solution. So remember, if this were pure water, it would be it should have been milliliters, my bad. Let me correct that. So milliliters, grams. If this were pure water, it would be 1 milliliter for 1 gram. 1 to 1. We learned that equivalency that's only true of water. 1 gram equals 1 milliliter of pure water. But this isn't pure water. It's got salt mixed in. So it's 1.027 grams for every 1 milliliter. It's not just 1 to 1. So that's something, that equivalency, or those conversions are something, this is basically a conversion factor. Okay? It converts from grams, which is mass, to milliliters, which is volume. How much something weighs to how much space does it take up. Okay? Now, it's comprised mainly of sodium chloride, so we only have one solute, that's sodium chloride. What is the molarity? We wrote that down already. That is 3.5 mass percent sodium chloride. So what does that mean? What does mass percent means? It means the grams of the solute over the grams of the solution times 100%. Now, here's the trick here. When you're given a mass percent like this, you can choose any mass that you want, any mass of the solute and any mass of the solution that you want, as long as when you divide them, you end up with 3.5 or 3.5%. So the simplest one to do, the one you should always use, is 100. You're going to choose to use a 100 gram sample of the solution, of the seawater. So we're going to come over here and we're going to write 3.5 grams of NaCl over 100 grams of seawater. That's the solution. Okay? Now look at that. 3.5 divided by 100 is 0.035 times 100% is 3.5%. So this is a 3.5% solution. Okay? the NaCl is 3.5% of the total solution. I could have written 35 over 1,000. That would have also been 3.5%. I could have written 350 over 10,000. That would have also been 3.5%. But why work with really big numbers? Let's just pick a nice reasonable number, 100, and that's always going to be the sample size you select when you have a percent mass problem like this. They say 3.5 mass percent. Fine. I'm going to take a 100 gram sample out of the ocean, and 3.5 grams of that, if it's a 3.5%, 3.5 grams of that will be NaCl. So that's a trick that no one ever figures out on their own. They have to be taught that, okay? Okay, here we go. So where are we? We have to get from grams of NaCl to moles of NaCl, and I can see still I'm not leaving myself a lot of space here, so I'm going to erase that for right now. So it's grams to moles, okay? And for NaCl, it's 58.44. So I'm going to write that up here. So I have the equivalency, so I'm going to come over here, and one of them goes on top, one of them goes on bottom, which is which. Again, we're solving the top first. Forget about the bottom. We're solving the top. So we got grams I needed to turn into moles. So I think we all know how to do that now. Grams of NaCl, grams of NaCl. Now I have moles of NaCl on the top. That's what I want in my final answer. So I'm done with the top. Don't have to do anything else with the top. Now I need to get from grams of solution to liters of solution. Okay. Now, if it was water, we know that 1 gram equals 1 milliliter, and that would make it kind of easy. But it's not water. It's a mixture. So where do we have a relationship between, we don't have anything with liters, but we have milliliters, okay? Where do we have a relationship between grams and milliliters? Well, we come back up here. That's our density. So we need grams to cancel out. So which one are we going to use here? The first one or the second one? We're going to use the first one. We need grams on top. So it's times 1.027. So it's grams of solution, grams of solution. Now I have milliliters of solution. I need to get to liters of solution, and that's our simple, this one. Milliliters of anything equals 1 liter of anything. So I'm going to put that here. I'm not going to write the units. Well, I better. Again, I didn't leave myself enough space here. Get rid of this. I'm going to write it way over here. Okay, so it's going to be okay, so milliliters of solution, milliliters of solution. So now I have liters of solution on the bottom as my only unit, and moles of NaCl on the top as my only unit. So I've got everything set up correctly. So it's 3.5 times 1 times 1.027 times 1,000 divided by 100 divided by 58.44 divided by 1 divided by 1. Okay, and that's going to get us to our final answer. And what we get is 0.615, and it's moles of NaCl over liters of solution, but we're going to write it as molar. Okay, there it is, and that's your final answer. So I give you 2 more problems like this. If you can master this problem, then you're really well on your way to doing any solution stoichiometry problem. Again, the complications in this were 2. You have to understand that this density, grams per milliliter, is really a conversion factor. Whoops, I'm on this one. 1.027 grams per milliliter for every 1 milliliter, and you can flip that over and make that into 2 conversion factors. The other thing, and this is a key one, if you're given a mass percent, you can pick whatever sample size you want to use. And you're always going to want to use 100 grams of the solution. If you have 100 grams of the solution, that's the salt and the water together, and it's a 3.5 mass percent, then that means you're going to have 3.5 grams of the salt. Again, you can just go back and do the math on that and figure that one out for yourself. 3.5 grams of the solute over 100 grams of the solution times 100% will give you 3.5 mass percent. So that's how you deal with a mass percent. Okay, so you do the next two.